Hey everybody, so what we're going to talk about in this series of videos is we're going to talk about how we're going to graph our complex numbers. We're going to graph them on the rectangular plane, our regular Cartesian coordinates, sort of, and then we're going to put them into polar form using trigonometry. It's going to be very, very, very cool. You're going to get a big kick out of it. I almost can guarantee it. So we can't really graph complex numbers on an XY plane. Because we can't order our pairs because I'm not going left and right. So what we're going to do though is when we organize them, we're going to use a rectangular coordinate system instead of our traditional Cartesian. So we are going to do an A plus BI in our rectangular form where we are going to focus on A, which is my real portion, and B, which is my imaginary portion. So remember, A is the real value, and B is my imaginary value. So our rectangular coordinate system is going to look a lot like our Cartesian form, our Cartesian grid, except the x-axis is my real axis and the y-axis is my imaginary axis. And we can take my complex number and we can write it as a vector. Remember, a vector has a starting point, it has magnitude, and it has an ending point. That's the magnitude is the length. So it has direction and length. So we can see here my real value on this vector is a 2. So on the real axis, we're going to go over 2. And then my imaginary portion is -3, which means we're going to go down 3. So that is my magnitude is going to be the length of this vector, and the direction this vector travels is 2 to the right and 3 down. So let's try that. Let's graph our complex number on this rectangular form. Remember, x and y really aren't x and y in rectangular form. This is my real axis, and this is my imaginary axis. Imaginary. Forgot how to spell it for a moment. So let's write this as a vector on my graph. So we are going to graph the vector -3, -5. So that means we're going to go left 1, 2, 3, and we're going to go down 5. 1, 2, 3, 4, 5. We are looking at this vector. Oops, I like straight line tools. Boom, right there. That is the value we are talking about. Or not the value, but the graph we're talking about. What if a part is missing? What if, and it'd have to be the real part missing, because if it was only imaginary, if it had no imaginary part, it'd be real and we wouldn't have these issues. So let's graph 6i. Well, another way of writing this would be a plus 6i. Well, there is no a. The value of a is non-existent, so we would say 0. We're graphing the vector 0. Oops, it's a vector. Come on, get with it. 0, 6. So from my origin, left, we're not going to move on the real axis. We are only going to go up on the imaginary axis. So we're going to go up 1, 2, 3, 4, 5, 6. And we're going to draw in that vector. Boom, easy. So if you can graph on a regular plane, you can graph on a rectangular coordinates. Well, what if we want to use what's called a polar coordinate? So a coordinate polar form, or our polar graph, will give us this as my, it's not really going to be an equation, but that's how we're going to write it, where r is, of course, the radius of any unit circle. R is the radius. This will be the magnitude of my vector, or the distance from the center. So this is going to be the distance from my origin, which is the center. Cosine theta will tell you how far on the real axis to move. And remember, my real axis is my horizontal axis. And then sine theta, see the I? The sine theta is my imaginary axis. And my imaginary axis runs vertically, because remember, cosine is an x movement and sine is a y movement. Another way to write this whole thing, these theta values, these angle values, are going to be the same for both cosine and sine. So we can often shorten this up to say z equals r cis theta, where we have cosine, an imaginary sine of theta. All right, so let's graph this. Let's graph this in polar form. So we want to go to the angle at 135 degrees. So from our origin, we are going to travel around 135 degrees to right here. So we're going to travel around that far to 135 degrees. Well, how far out from the origin are we going to hit this 135 degrees? Well, we're going to go out a radius of 5. So 1, 2, 3, 4, 5, right there. So here is the graph on my polar coordinates. Boom. It has a magnitude of 5, and you can see we opened up 135 degrees. It's like a unit, just like a unit circle. Notice again, theta and theta are the same. This could have been written 9 cis 330, 9 cosine of 330, and imaginary sine of 330. So we're going to go to 330 degrees, and we are going to come out radius of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Don't forget to put in your vector. Not bad, right? I actually think that that's a great place to name it, because now what we're going to do is we're going to take what we talked about from our polar coordinates and our rectangular coordinates, and we're going to put them together. That's going to be in the next video. Just wanted to give you a little heads up. So if you have any questions, please come in with those questions. I'd be glad to answer them.